think it worked out nicely. And he's from the V8 team. So he made the way from the Munich office over here. Thanks for joining us, and I'd be very happy to listen to your talk. How many compilers is too many? Please tell us.
Fantastic. So I maybe will not be answering this question fully directly, but I can tell you how many compilers have worked for us. First of all, like when you're designing a system, you have to think about what the actual constraints of the system are. For JavaScript specifically, basically everyone wants it to be everything. It has to be fast in execution, peak performance. It has to be fast in startup and loading. It has to be efficient in memory. It has to be easy to debug. It has to be dynamic as a programming language. It has to be monkey patchable, among those things. It obviously has to be secure because you don't want your bank to send all your data to an unknown third party. And it has to stay modern and updatable. And standards body keeps adding more and more features to it. And people want to have those features as soon as possible. And what we've landed on currently as a structure for the compiler, for V8, for compiling JavaScript, is that we have an interpreter called Ignition, a baseline compiler called Sparkplug, a somewhat optimizing compiler called Maglev, and an even more optimizing compiler called TurboFan. And I'll be using these names throughout the presentation, so remember this slide. But it hasn't always been this way, right? We've slowly figured out how many compilers is too many. And we've actually gone through a long history of various different compiler configurations, which have all been driven by the needs at the time and driven by, well, what we learned while developing the previous layer of this cake. Now I've been given actually 45 minutes for this talk, so I can start a little bit earlier with when JavaScript was first introduced to the world. So 1995 is a long time in the past. Batman is unironically played by George Clooney. Windows 95 is getting people very excited, and the best graphics for a video game console are on the PlayStation 1. And the internet is somewhat of a new thing, and not necessarily everyone is very optimistic about its success. The cool kid on the block is Java. I don't want to say this is not still cool, but at the time it was definitely very cool. And Netscape, the browser, which is something that existed back then, asked this guy, Brendan Eich, to come up with a scripting language for the browser so that their browser could do interactive internet stuff. So this guy came up with something called Mocha, which was later renamed to LiveScript, which was later renamed to JavaScript. And this was developed originally, I think, in 5 days for the first working prototype. And it's a cute little language. It's got addition of integers. You've got addition of strings with the same addition operator, which means you have this already implicit operator overloading. You have addition of anything with anything, really, which does type conversions as necessary. These type conversions are user hookable, so you can convert something to, you can have an addition of an object which has a string property or a value of property. They do slightly different things, but also really the same thing. Just because it's called toString doesn't mean that it actually has to return a string because it's a dynamic language, so this name can lie. And potentially you can also return something that then again has to be type converted, which means that it's fully user hookable in every possible way. There's not really a way to statically analyze, for example, the addition operator without analyzing the entire world, the entire program, the entire context that you're running with, all possible forms of user input. So basically something that cannot be optimized like that. Now, JavaScript engines are something that takes JavaScript source code and emit a value, effectively. An interpreter for the JavaScript language could parse this into an AST and then walk this AST to interpret it and then return that value. Much more commonly, it would compile that AST into bytecode and then interpret that bytecode to come up with a value. And indeed, the initial JavaScript 5-day prototype was already a bytecode compiler I discovered when doing research for this talk. So this has been a bytecode interpreted language from the very start. 1996, this was standardized. It was standardized under the name ECMAScript, which is the European Computer Manufacturers Association. Really, it's JavaScript, but because of the trademark issues, it couldn't be standardized as that. Again, I did a bit of digging. There were some other names proposed for it as well at the time when people were trying to figure out a name. This one really, for me, highlights that this was the 90s. But yeah, JavaScript was used on websites to do little bits of interactivity, a little bit of a spinner, a little bit of a calculator, this sort of stuff. Okay, 1996. Fast forward a little bit into the future, into 2005. 2005, Batman is now played by Christian Bale, thank you. I was about to say Christopher Nolan, that is not the actor. Windows is now all the way up to XP, which is an actual functional Windows version. And the Xbox 360 is now providing graphics that, can actually be used for playing video games. And, the internet actually exists as a legitimate thing that has legitimate websites that you can actually use. Like, they still look, maybe a bit old, but not nearly as dated as the Amazon picture from earlier. And Google, for example, but not only, is doing a lot of work into actually making this into a proper interactive computing platform and not just a way of displaying documents. I don't know if you remember MapQuest from 2005. This was how maps were presented. And these things, north, east, south, west, were actual links that you would click that would take you to a different page that would show you another section of this map. It was the best that we had at the time, but it wasn't like super usable. Google introduced Google Maps, which is a whole different level of interactivity for this sort of thing, and needs a whole different amount of computing power. Around the same time, we also got this concept of AJAX, asynchronous JavaScript and XML, as coined as a term. And this was actually based on older technology, and technology from the year 2000, from Microsoft in Internet Explorer. Like, don't say that Internet Explorer didn't innovate anything. Internet Explorer actually brought us the modern web. And this was invented for Microsoft Outlook on the web. It's a fun bit of history. And around this time, we started getting this JavaScript renaissance of JavaScript frameworks. jQuery was started off in around this time. The prototype library, which I don't think is now dead, but for a while was very popular. MooTools. In 2007, the iPhone came out. And one of the things that I notice here is that actually one of the first selling points, the very first thing on this particular slide, is that the iPhone was designed for Web 2.0. And AJAX, this idea of web apps rather than websites, was really growing in this time. And you started getting books written about how to program in JavaScript, JavaScript the Good Parts, which is a much smaller book than the JavaScript book itself. So 2008, like I say, Google is investing a lot into this whole web JavaScript thing. And out comes Chrome and V8. V8's job is to make JavaScript fast. How does it do this? It does it through a combination of native code and of inline caches. Native code means that where we previously had compilation from AST to bytecode and that bytecode is interpreted, now we have compilation of that AST into machine code, and that machine code is run. And this was the very first version of V8 in 2008. This was the only compiler that we had. I can definitely tell you how many compilers is too few. One was not enough, but it was pretty good. Another reason it was pretty good was because it used something called inline caches. Inline caches are based around caching information about a concept called hidden classes. Hidden classes means that if you have something like this, an addition of two values from a point class, a class that has X and Y, semantically in JavaScript, it's a dynamic language, it's a monkey patchable language. This is conceptually just a dictionary. So it's an object that points to a dictionary. This dictionary maps strings into values. If you have a second object like this, it has a completely separate dictionary semantically, which maps strings into values. And this is all good, but when you actually want to access these, then you have to do table lookups, dictionary lookups, hash table lookups, however you want to actually implement it. You have to go into your object, you have to dereference the dictionary, look up the value of the dictionary, et cetera, et cetera. So hidden classes means that we look for patterns in the shapes of objects, meaning that this JS object, for example, is an object that has two values in it, 1 and 2, and those two values are named x and y. So we define a hidden class, what we call a map, which says that field number 0 is called x, field number 1 is called y, and then this map defines the shape of the object. The object itself contains the value of those fields. If you have two objects which have the same shape, then they share the same map, but have different values stored in objects themselves. What does this mean? This means that when you have your lookup of your property, you look up your property x in here, then you dereference your map. You look, where is my property x in my hidden class? It's at field offset 0, so I look at field offset 0 in my object to get its value. If you then pass in the other object into the same function, well, it has the same shape. You can look up the field offset in the same place. So the idea of inline caches is to somehow cache this information so you can reuse it for future lookups, under the assumption that you're always going to pass the same shape into the same functions, which is normally the case if you're writing in at least reasonably object-oriented style way. So CodeGen at the time would emit machine code, which would, this is a V8 talk. V8 talks always have to have assembly in them. Emits code that looks something like this. The important part here is that it loads some unnamed property at first, and then does some unknown addition operation on them. When it does this unknown property load, it figures out what kind of load it was doing. Then it generates a cached handler for that kind of load and patches the code to always try to load that kind of shape. And then it can make fast code here and then bail out if it didn't get the same shape at the same time. So if there's no match, then it bails out. Otherwise, you can receive the same object multiple times and emit this, call this fast code that always loads the same field offset from the same kind of shape of object. Thanks to this, V8 at the time was a lot faster than other engines. This is also from a benchmark that V8 generated. There were other benchmarks at the time. Here now smaller is actually better. And SpiderMonkey, TraceMonkey, the Firefox optimizing compiler, also at around the same time, was also actually starting to implement the same kind of optimizations. It was using a tracing JIT at the time. It was also using hidden classes. It was also using inline caches. And the reason is because this isn't exactly a new idea. This paper is from, I think, 1984. This is from 1991. These are reasonably standard, actually, in the literature, optimizations for dynamic language on Smalltalk himself, respectively here. But that's all good. JavaScript is now fast, right? Well, yeah, it's fast. It's faster. Is it memory efficient? I mean, kind of. You're generating like a bunch of this machine code. So, but then you're offsetting that by generating hidden classes instead of dictionaries. So it's kind of like when you win some, you lose some, right? Is it secure? I mean, Jesus, right? Look, it's generating machine code. Like, how secure is it going to be? But it's not bad. 2010, it's fast. Could be faster. We introduced a compiler called Crankshaft. And CodeGen becomes full CodeGen because it wants to compile more kinds of stuff. Now, the way that CodeGen was working in 2008 was that you were compiling semi-optimized code from an AST. The way that Crankshaft started to work is that you were first compiling your full CodeGen code into unoptimized code. Then after a while, if you realized that a function was hot, you would optimize it into Crankshaft, which would then again reparse the source, reread the abstract syntax tree, and generate optimized code. This optimized code could potentially de-optimize into unoptimized code. What does this optimizing, de-optimizing mean? Well, if you think about what the full CodeGen code looked like with the patching, you had all these sort of calls. You would do patching on these calls to make them faster, but they would still be calls. You still have stack manipulations, random stack loads, these sort of things. It was like fast, but could be faster. what Crankshaft did was take the sort of contents of these handlers, effectively, and inline them into the code. So if I just skip through a few slides here, in Crankshaft, we would first check the map, the hidden class of our inputs. If this matched, well, if this doesn't match, then we de-optimize. If this does match, well, then everything's gravy, right? Like we can just do an addition, or we can do a load, we can do an addition, and we're done. Like this is all the code that you need, as long as you get the right shapes. If you don't get the right shapes, if you get one of these user hookable transformations, then you do this de-optimization. And the de-optimization basically means go back to code gen, re-execute from the same location in code gen. From the same location is a little bit tricky here because that means you don't want to have side effects executed twice. So each part of Crankshaft have to know how to de-optimize back into the appropriate part of full code gen, which effectively meant that you had to do an abstract interpretation of your full code gen and then figure out what kind of code full code gen would have emitted and then perform a frame-to-frame translation here. It's a little bit annoying, but it's completely doable. And this idea of de-optimization sounds scary, but as one of my colleagues said, de-optimization is the most important optimization that V8 has, because thanks to the ability to de-optimize, we can generate much more optimized speculative code. And Crankshaft was very good. Again, on benchmarks, Crankshaft was like the first improvement that we had in V8 in several releases. So this was what made V8 fast at the time. It was way faster to run. It was faster to start because the full code gen didn't have to do as many optimizations as Crankshaft had to do. So we could sort of dial back on optimizations the full code gen was doing. It was less memory efficient. That kind of sucks, but you're generating even more machine code. Fine. Security, Look, we're generating machine code and now we're optimizing it as well. Is it debuggable? Is it modern? Is it easy to maintain and to keep it modern? Also a little bit difficult. Like I mentioned, we have to rework the same AST, figure out how to do these de-optimizations. It's messy. It's doable. The debugging, you want to set breakpoints. Those breakpoints you can't set in Crankshaft. You probably want to go back to full code gen and de-optimize there. Again, all doable, but tedious. So fast forward, 2016. I promise I'm going to stop doing the Batman thing after this slide. But at this point, Batman is Ben Affleck. Windows is on Windows 10, which it was almost eternally then. And the Zelda console is selling out at the time. And this is around the time where we introduce Ignition, the interpreter. And this is basically what's old is new again. What we were doing was generating this native machine code using CodeGen. What we do with Ignition is go back to bytecode. It might seem like a step back from where we were before, but it's got very good reasons. Ignition was actually started as a project for mobile, for Android, because we realized that the memory efficiency was especially a large problem there. And Ignition was supposed to help with that by first generating bytecode, which was a lot more compact than the machine code that CodeGen generated. And we did see legitimate memory use half on mobile. Actually, memory use half on desktop as well, because why wouldn't it? It's the same browser. What was really interesting though with Ignition is that startup time for websites also improved. Because it turns out compiling things to bytecode is a lot cheaper than compiling things to machine code, right? And then the interpreter costs, they're higher, but what you're doing at startup a lot of the time is still that compiling. So the two cancel out and cancel out in favor of the compilation, especially because it was main thread bound. So it's not just memory efficient, it's also fast to start.
Quickly switch out the microphones.
Yes, of course. If I go over now, it's beautiful. If I go over time. Yeah. What else did we want from JavaScript? We wanted it to be fast to run, and we wanted it to stay modern. Like I said, Crankshaft was hard to keep modern. You in fact had a lot of these concepts of optimization killers in Crankshaft. And lists of reasons why function optimization would bail out things like async functions introduced in 2016, I think. And for Optimum construction also introduced around the same time. Exception handling, try cache. Crankshaft didn't handle any of these, and people had to write their code in what we call Crankshaft script to keep it fast. So we started thinking about an alternative compiler to Crankshaft that would be a little bit easier to maintain. Introducing TurboFan, our Sea of Nodes compiler. Very exciting. Sea of Nodes was like the can I say new idea around the time? It was a trendy idea at the time, which was a different way of representing IR than CFG, than basic blocks. It was that everything that you have is some sort of free-floating node, and these free-floating nodes are connected with various kinds of edges, and then those edges have to be scheduled somehow in some sort of topological sort, so that they're ordered with each other, but things could float around randomly, and suddenly all your code motion and your compilation would be very easy to do because it would come for free, effectively scheduling. So something like an addition operation would actually be a free-floating addition of two values, multiplication, and subtraction. These are all value edges into value-generating nodes. And you return a value, and there's no control flow concept here at all. This is entirely a value graph. With control flow, you would have explicit control flow nodes. So you would have your value arithmetic free-floating, but once you had a branch, that branch would generate a control flow graph for just the control flow nodes. And the way the values would be injected into that control flow is, again, by scheduling them afterwards so that all these edges always keep pointing forward. Control is not necessarily the same thing as side effects, so you might want to maintain that like your stores happen before your loads, or vice versa, or before other stores. And the way that these would be scheduled was by having effect edges between them, side effect edges that would maintain that ordering. And this is not control flow, this is effect flow, and it's independent of control flow. This is a theoretically very nice idea. And the two could mix with each other. So you could have a load, which is on the effect chain, you could have a branch, which is on the control chain, and you have a control chain for the branch, you have an effect chain for the load, and again, magically the scheduler would figure out how to make sure that these things work for you. But the two chains are nominally independent of each other, and in particular, this load could happen before or after the branch, which is kind of interesting. Turns out that we don't actually necessarily want loads to happen before the branch that decides that load should happen. So loads do end up participating in the control chain. Maybe a little bit on that later about how good Sea of Nodes ended up being for us. But for now, it's 2016. We're very happy with this. And this optimization killer's idea is dead. Like TurboFan is now easier to add stuff to at the very least. And we can add exceptions to it. We can add all these new fancy features. And around 2017, we launched Ignition and TurboFan. I said 2016 because just before this, we had a soft launch, if you like, of Ignition, where we still wanted to have the performance benefits of Crankshaft, which was at the time still faster than TurboFan. We still wanted the performance benefits of full code gen, even on mobile. And we had this thing we called the Franken pipeline, which had everything kind of being able to optimize into everything else and de-optimize from everything else. Thankfully, a year later, we managed to get rid of this by doing enough work on Ignition and enough work on TurboFan to allow them to match the performance of what preceded them. So JavaScript is now fast, all around, memory efficient, secure, modern, right? Fantastic. But is it? Is it fast to run? But around this time, we're using benchmarks to analyze this. We're using Octane, developed in, I want to say, 2012. And this was supposed to be, directly translate to a better and smooth performance in web applications. Like, this was supposed to be a realistic benchmark of what people actually do on the internet, what people actually do on actual websites. If you look at an actual website, though, the story is not necessarily as clear as how Octane makes it look. Octane is exercising the TurboFan compiler fully. It's a peak performance benchmark for the TurboFan compiler. But an actual website spends a lot of its time in in bytecode because we do a lot of startup, right? Like all this execution of startup time before the optimizing compiler warms up. Websites aren't doing 1,000 iterations to get to peak performance. They're executing straight away. What's worse, TurboFan here is, I mean, this is this sort of cold graph, right? TurboFan is the top thing there. The bottom thing here is things that TurboFan is calling and didn't actually manage to optimize away. So actual self time in the TurboFan compiler is very, very low on this particular example website. We spend a lot of time in ignition and things that ignition calls, and a lot of time in various helpers. And sure, there's like some sort of sampling bias here, because if TurboFan is faster, then we're going to spend fewer CPU cycles in it. But still, right? Like, we're not spending that much time. I think in this particular trace that I did yesterday, there was 0.01% of cycles were actually being spent in TurboFan code itself. Another problem, if we zoom out a little bit, is that TurboFan compilation takes up a lot of time as well. It's not really paying for itself. Like the time we're spending compiling TurboFan and the time we're spending running TurboFan, incomparable, right? This is happening on the background thread. Not yet at this point in the timeline, but eventually this gets moved to the background thread. It's not the worst thing in the world, but you know, like with respect to CPU cycles, there's still CPU cycles. And the problem here, right, is that the compilers effectively are trade-offs. We found two spots in the trade-off space. We found ignition right at the very start, which is, you know, it doesn't give you much benefit from compiling, but it compiles fast and it's low risk. And on the other side of the trade-off space, we have TurboFan, which gives a lot of benefit once it's compiled, which is why it's very good at these peak performance benchmarks. But the risk that you're going to de-optimize, the amount of time you're spending on it, the amount of CPU cycles you're spending on it, all these sort of things are also high. And in the middle of this trade-off space, we've got nothing, right? So how many compilers is too many? Well, these two are not enough to fill this trade-off space. Around the same time as well, we started retiring Octane because we started realizing that this is not a benchmark that's good for the web. We started using actual website traces, actual website recordings. In terms of benchmarking, we started using speedometer and Jetstream, which we still use to this day. These are benchmarks actually developed by Apple. Now they're both going to be in open governance and going to be maintained by all the browser manufacturers. So it's not like an individual browser manufacturer saying, hey, I wrote the benchmark, look, and I'm fast on it. It's actually, you know, somewhat convincing as a story. So we started trying to fill that gap in the trade-off space. Our first attempt, not launched in 2020, weirdly enough, not that many Batman movies in that year, was Turboprop. Turboprop was basically TurboFan minus. It was switching off optimization phases in TurboFan, trying to increase its compilation speed at the cost of its compilation performance. Unfortunately, like the idea of TurboFan, the idea of this very generic optimizing compiler where you can switch phases on and off, would be that you could make these trade-offs dynamically, but there was still a lot of kind of fixed overheads in TurboFan. So even though Turboprop turned off a bunch of stuff, managed to compile earlier, did manage to improve JavaScript execution time. This is, I think this was our actual website. No, this was Speedometer. It managed to improve actual JavaScript time. It hugely bloated the amount of compilation time they were spending on this middle tier compiler. And in fact, our total CPU usage went up quite a lot using Turboprop, even though we've been turning off all these phases because we were now trying to compile more. So that didn't work out. That didn't get launched. So instead, we tried to approach this from the other side with a new baseline compiler called Sparkplug, right? Like Ignition, Sparkplug. I really like this code name. We sort of ran out of car parts eventually, which is why other code names aren't necessarily as good, but this one was still a good one. The idea of Sparkplug is that it's a non-optimizing JIT compiler, which is designed to be as fast as possible, no matter what the cost. The compiler itself is actually supposed to be just a single pass. It doesn't end up being obviously a single pass, right? Like it's like 2 passes or so. But it's a single pass that is that's just forward translating bytecode into machine code as quickly as possible. Input bytecode, output machine code, done. No optimizations, no nothing. No speculation as well, no de-optimization. And the way that it works is effectively you get your bytecode and we stamp out machine code for that bytecode. And the next bytecode, we stamp out machine code for that bytecode. Bang, 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 bang. This is the compiler. And you end up with this sort of thing. Every actual operation calls out into helper functions that performs the operation, right? This is just designed to compile as quickly as possible. These days, it will be called copy and patch, I guess. But it's just using a simple macro assembler. It's fine. It's very simple. Like we implemented the first prototype of this in 4 days. Me and like one other colleague, and it was great, right? Like it's seriously improved performance on speedometer. It's seriously improved performance on various actual websites. This is a very nice blog post that I wrote, so I think is great about this. Really great result. Sparkplug was in a great place in the Tradeoff space, filling the gap between Ignition and TurboFan. So where are we now? We're fast to run, we're fast to start, we're memory efficient thanks to the bytecode, although a little bit less memory efficient because of Sparkplug, but it's still not bad. But I mean, still a gap, right? Like how many compilers is too many? This isn't it. Like this, we can do better. And this is 2023. This is when we introduce Maglev. Maglev is our mid-tier optimizing compiler. And the idea here is that it's supposed to be optimizing, but optimizing not as little as possible, but as simply as possible, as quickly as possible. It's the fastest optimizing compiler in V8 is the idea. It's supposed to be an order of magnitude faster than TurboFan at the cost of being an order of magnitude slower than Sparkplug. And on the log scale, that kind of makes sense, right? It should be as simple as possible, no simpler. It is actually supposed to be optimizing. Sparkplug was a non-optimizing compiler. This one is optimizing. It can de-opt, but those de-opts are cheap, quotes, because re-optimizing into Maglev should also still stay cheap. And the design idea here is that while TurboFan has multiple different levels of IR and multiple different phases that operate in those levels and various lowerings that transform one level of IR into another one, phases that are kept independent of each other because of good software design. Maglev doesn't have good software design. It has good engineering design instead, where there's a single IR for the entirety of Maglev. And the phases try to do just as much stuff as possible in that phase. And they try to do it as much forwards as possible. This is the as simple as possible, but no simpler. So most optimizations in Maglev are effectively forms of elimination. Like if we've done a load before, we remember we did that load. If we do that load again, we don't omit it, right? Like the simplest kind of load elimination you can do. It's not necessarily fantastic around loops. We try and make it kind of okay around loops. Whatever, it's good enough. Wherever it's not good enough, TurboFan will be, right? Like it doesn't have to be good, because if it's slow at something, eventually we'll get to TurboFan anyway. And in terms of optimization time on a log scale, right? This is how you can see that I'm actually a computer scientist and not just an engineer. It's right smack bang in the middle. Like TurboFan takes this amount of time, Sparkplug takes that amount of time, Maglev, bang in the middle. This is exactly where we want it to be in the Tradeoff space. And it's good, right? It's making trade-offs. It's not necessarily generating as good code as TurboFan, but it's generating a lot more quickly. And because we're generating good enough code pretty quickly, now TurboFan is not as necessary early on as possible. So now we can push it out further, which means we can take more risky optimizations. We can speculate harder. We can spend more time on more advanced, different kinds of optimizations, more advanced analyses. And it doesn't matter, because if we need that peak performance, we'll get there eventually, and then we'll have it. If we don't need it, then Maglev is good enough. So on those two benchmarks that I mentioned, speedometer and jetstream, TurboFan and Maglev was a distinct improvement. Like these are single-digit improvements, which might not seem as much, but these are like benchmarks that we've optimized for a long time, right? Like at this point, we're fracking for improvements here. And more importantly, compile time, as importantly, compile time goes down significantly. Why does it go down significantly? A combination of factors. A, we can push TurboFan out further, like I said, so we're not compiling TurboFan as much. B, because deops are cheaper, normally if we de-optimize TurboFan, we would have to re-optimize into TurboFan. Now if we de-optimize whatever optimized code, we re-optimize into Maglev. And if we're going through these like deop cycles where we're learning more and more about our program, each time we have to recompile less. So that's great. And actually Maglev by itself on speedometer, actually it's almost good enough by itself. It's not as fast as the combination of the two, of those two optimizing compilers, but it is faster than just running TurboFan by itself because of that compilation speed advantage. On Jetstream is much more of a peak performance benchmark, so just Maglev isn't as much of an improvement, but hey, I mean, like, it's 1/5 of the compilation time. It's not bad. Also on real websites, again, like a couple of example website recordings that we took. It's a solid improvement on time, very solid improvement on optimization time. JavaScript is fast. It's fast to run. It's fast to start. It's secure. Is it secure? Okay. Now, those TurboFan graphs that I showed you earlier, like this, I mean, how many people are happy with this view of a graph, right? If I add some more things into my program, how many people are happy reading this graph and telling me that there are no bugs in it? Hard to say, right? If I look at a sea of nodes graph for a function with a single instruction, this is a real graph now with the appropriate sort of conversions that we have to do, the appropriate kind of speculations. You know, this is a lot of nodes to analyze for any particular operation. Like an equivalent CFG graph would be a lot simpler. It's a lot of nodes, but at least the conceptualization of how the execution happens is a lot simpler. If you have more than one instruction, well then, good luck, right? And the equivalent CFG graph, while still complex, is a lot easier to read. If we want to talk about concrete security problems that we have had with TurboFan, I mean, this like control and effect chain play is very nice for scheduling, it's very nice for code motion, but you better get it right, right? Because if you have a string concatenation is a pure operation, right? Like you add two strings together. This should be fine. But if you have control flow, that's making sure your string concatenation does not go out of bounds of your maximum string length in the VM. Maximum string length is not a very pure operation, right? But this is a real problem in real production VMs. You know, you want to make sure that your concatenation happens after this safety check. The way that we do this in TurboFan, this is actually the way that we do this, is that we effectively have what we call type guards, which merge together value flow and control flow, and guarantee that your value that you're checking is within some safe length. If you have perhaps some sort of constant folding style optimization, and that constant folding style optimization doesn't take into account type guards, you now have a free flowing string concatenation, no longer attached to this control flow, which can go out of bounds on a string. This is not good. This is the sort of security errors that we get. And yes, every single one of these is fixable, but these things are very difficult to reason about. And you might say, okay, skill issue, get better as engineers, and you might be right, but you know, experience has shown us that we're just not smart enough to figure out how to make sea of nodes safe. So 2024, we start working on TurboShaft, which is a combination of TurboFan and Crankshaft, at least in terms of naming. And the idea of TurboShaft is that we're going back to CFG. We're giving up on this whole sea of nodes thing. And these CFG graphs that I was showing you earlier are now what our actual TurboShaft graphs look like in the modern day. Maybe something that's interesting about TurboShaft is that normally if you have an IR, then you would be doing some sort of transformations on it, reductions, lowerings, and you would go from one, you would do some modification to your IR in your one phase, you do some modification to IR in another phase. This is not necessarily super cache efficient, and you're changing most of your IR most of the time if you're doing lowerings. So what TurboShaft does is it sort of takes a page out of garbage collections book, out of sort of these scavenging semi-spaces, and it has two effectively semi-spaces for its IR, and it copies between them, because it turns out memcopy is fast on modern computers. And if you're replacing most of your graph most of the time, then it's not going to be any worse than doing it in place versus copying it somewhere else. So your first phase will copy your entire graph and apply reductions into the other semi-space. Your second phase will copy it back into the first one. This means that we have to use IDs instead of pointers, but again, that's actually not a bad thing. On 64-bit systems, pointers are 8 bytes. We can use 4-byte pointers, so your whole graph becomes more complex. And this is way more cache-friendly than something like TurboFan is. Indeed, this is like the number of data cache misses, one data cache misses that we had in JetStream 2 before and after. It's like a 3 times reduction in one cache misses. And memory is the slow thing in computers, right? Computing is fast. Memory is slow and expensive now. So great. But the thing is, like, this is, well, this is only true if you're not doing in-place transformations. So on your back end of your compiler, where you're lowering all your operations into machine code, or some sort of machine code IR, and then you're rest allocating that, and then you're lowering that into actual machine code. These sort of operations are very efficient to do with copying IR. If you're jumping around randomly in your program to do optimizations, maybe less efficient to be copying the entire graph for every single optimization or inlining or whatever else that you do. So finally, in the present day, what we have is 2 projects in progress, Sparkplug Plus and TurboLev. TurboLev is a combination, as a code name, of TurboShaft and Maglev. Now, what's the idea here with TurboLev? Okay, right now, this is what the 8 looks like. We've got ignition compiling bytecode. That bytecode gets passed into Sparkplug, into Maglev, into TurboShaft, and it will generate some code or another. The problem with this is that basically every optimization that we want to have, we have to write twice. We have to write it once in Maglev and once in TurboShaft. So the idea of TurboLev is to combine these two, is to feed Maglev into TurboShaft and share the at least front-end optimizations that we have there, and then have TurboShaft just do the more advanced, additional, classic, if you like, compiler optimizations afterwards. So where previously we had a single Maglev IR like this for Maglev and the more complicated IR for TurboFan/TurboShaft, the idea of TurboLev is that we can share the single Maglev IR between both of those, and then either we go into a Maglev backend, which is very, very simple and basically is just stamping out machine code, or we do a couple of more optimizations, we do a bit more inlining, we transform this into a TurboShaft graph, which is much more amenable to these sort of classic optimizations, and then we finish off in TurboShaft to generate assembly. This is an ongoing project. I don't have any numbers to share yet because they're not as good yet. But we're hoping to get this launched sometime this year. The other project that we have is Sparkplug Plus. This is actually being contributed to us by Intel, which is lovely of them. And the idea here is that, you remember this is what Sparkplug looked like, right? Like you had your bytecode, you had your generic Sparkplug code. The idea here is that, well, you have these generic calls. If you were paying attention about, I want to say 40 minutes ago, then you realize that these generic calls could be replaced with specific calls through code patching, right? And then these specific calls could check the map. If the map matches, it doesn't match, then bail out. Otherwise, do the appropriate integer subtraction. You know, no complex lookup of whatever else is. Just pass subtraction return. And you'll be saying, like, haven't you gone full circle here? Like, haven't you just done full code gen again? And I would say, like, yes, we've done full code gen the way it was supposed to be, because we still have the advantages of the bytecode, and now we have the performance advantages of native machine code generation with patching. So we've gone from, reasonably fast to run, to start, for security, into something that's pretty good along all axes in the trade-off space. How many compilers is too many? I think this is the right amount so far, but I'd be happy to take questions.
So it seems we have a couple. Do we need the microphone still? Or?
There's no one on the Zoom, so
Okay, so that means we can do without microphone. Fortunately, my volume is out. Okay, can take any questions from the audience? Patrick, please.
First, I just wanted to mention 1995 Batman Forever. That was Val Kilmer.
Oh,
I wasn't sure. I thought it looked like Val Kilmer because I was watching Heat the other night. But anyways,
that's even more ridiculous.
Can you talk about what V8 actually uses as a representation for inline caches? Because I don't think it's not actually patching the code.
Not anymore. Around the time
originally it did.
Originally it did. Originally it only did code patching, and actually one of the benefits of Ignition, the interpreter, was that it wasn't just the cost of the code that was causing us memory costs. It was the cost of all these stubs that we were generating for the individual patches, because each individual inline cache that we wanted to patch was actually generated, like dynamically generated code that embedded the appropriate map pointer, that embedded the appropriate field offset, that embedded everything, and these had to be generated at runtime. So we moved around that time also to what we call data-driven ICs, where there's it's effectively for the bytecode. Actually, I wonder if the bytecode that I showed here has examples. No. But effectively, each of these bytecodes that has some sort of inline cache will also have a index into a vector of feedback. That vector of feedback will have some sort of encoding of what operations that bytecode has seen in the past. So for additions, this would be like a single enum, effectively, or what kind of additions have been seen. For loads, this might be like a simple bytecode in itself, like a simple bit field of this was the field offset, this was the map, it was a known property, that sort of thing. Or it might be like a more complex object, but still a data structure that defines how to go up, let's say, the property chain to access that object, or whether it was maybe a constant that you can just reload the same constant every time. But yes, we had to move away from patching, obviously, for Ignition, because we weren't going to be. We also wanted to move away from the costly machine code stubs. With Sparkplug Plus, however, these handlers are still statically generated. So we'll have a couple of handlers for things like this is a load at field offset 0, and field offset 1, field offset 2, field offset 3. This is going to be embedded in the binary, and generic field offset. And the idea of these faster stubs is not that they embed, for example, map information, but they still read off the data-driven ICs from the feedback vector, but just skip a couple of steps, or skip a couple of branches in the interpretation of that, or reorder them to make them more efficient.
Cool, thanks. And by the way, I think inline caches actually predates self, right? They were done in Smalltalk, so before hidden classes.
That might actually be the case. I'm going to be honest with you here. I'm an engineer. I'm not a programming language researcher. Programming languages is not my background. I've worked on V8 for about a decade, but I've not worked on any other VM before that. So my idea of the literature is mostly picked up by osmosis and from doing small amounts of research for talks like these. So it's very likely that, that I've missed some past work.
Small. You might have shown one of the papers.
Yes,
that it came from.
Papers from 1984 from Peter Deutsch and
yeah, exactly, yeah.
Implementation of small.
Yeah, well, that's the inline caching paper, and he had the polymorphic inline caching paper.
But the left
that's the other
Deutsch.
polymorphic inline caching itself, right? Yeah, exactly. Yeah.
How many slides did I give you?
There
There we go. Yes, this one was self.
Yeah.
And
This one was
no, the left one is small talk.
Small talk. Sorry, this one was self. This was Osvaldo. He's currently our head of cloud.
Yeah.
We have we have around.
We have loads of time.
Okay. Okay, Felix, please.
Was the move away from the graph IR to non-graph CFG really just a human comprehension problem that it was difficult to understand the graphs, or were there also
not only? We've actually got a blog post on this one called Land Ahoy, Leading the Sea of Nodes. A big part of it was also just the performance, which was mostly influenced, I think, by the cache behavior of the Sea of Nodes graph. Got on another presentation, I don't have the slides for it here. But effectively, like if you're doing all these in-place transformations of all these nodes, you end up scattering your graph all over everywhere. And suddenly you're doing all this pointer chasing just to do very simple transformation. Like let's say you want to do branch elimination. You have to walk all of your memory and do pointer hopping between all possible nodes to try and find these branches. It's just very inefficient in terms of cache behavior. On top of that, like I mean, there were these things would have been solvable with different IR designs. Like you could have had a copying IR for Sea of Nodes as well, in theory. Like the kind of optimizations that you want to do in it don't really lend themselves to this kind of like linear layout, but it's possible to do. So there was like a combination of factors, but human comprehension was definitely a big one.
Okay, any other questions? Stefan was a little bit faster.
So V8, of course, is also used in Node.js.
Yes.
And that use case is slightly different. So is that something you keep in mind, or is that a priority for you guys?
Am I allowed to talk about priorities? Like
it's all right, but then I will just ask.
No. This is a legitimate question. Like it is something we do keep in mind. It's not something we can keep as like a high priority, but we do like we don't want to kill it or anything like that, right? Like it's something that is very interesting to us. Also, just on a
But is that something where you also kind of keep an eye on use cases and their performance?
As much as we can. So the Jetstream benchmark, for example, includes a couple of benchmarks which are effectively node benchmarks. So one of the sort of sub-suites that it has is called the Web Tooling Benchmark, which is effectively node tools for doing whatever node is doing. Like we didn't take these because they're exercising node or node kernels. We took these because they're large examples of JavaScript doing stuff. But it's these sort of things that we still want to keep really reasonably performing.
So the worst case for just-in-time compilation system seems to me unit tests.
Mm-hmm.
So I think there are some people on the internet that I think for PyPy it was something like 70x slower than I see. The PyPy is a very specific way of doing things. Anyway, so do you think you have enough levels of compilers to do well on unit tests, or is the quality of the Sparkplug sufficient to basically make unit tests run reasonably well?
Unit tests, I actually would say, are more similar to the way that websites load than actually like a node server would be, because they have to start up, they run for a bit, and then the user closes the tab.
Well, they run exactly once.
Yeah, right, exactly, yeah. So, I mean, it obviously depends what you're unit testing. If you actually want to unit test the compilers, right, then
right. That's
something else. But yeah, I mean, like startup is a concern for us. If you load up a new tab, I'm talking in browser terms because that's sort of our most important client, so to speak. But it's the same sort of problem. Right. And if you want to start a web worker, which is a browser for a thread, you want that to start up quickly as well. So it's not the most important thing that we have, but it is definitely like something that we keep in mind.
But is that something you also measure, or? I mean, I haven't done any benchmarks on V8.
The way that Jetstream, for example, does its measurement is that it measures the first iteration, the other iteration, the average of the other iterations, and the worst 4 of the remaining iterations. And these scores all get averaged together. So the first iteration gets weighed as heavily as all of the other iterations. So in that sense, yes. Yeah.
Can you say anything about the WebAssembly compilation pipeline and sort of, yeah, if, I think I believe there are 2 tiers now, but whether there are more coming likely or not, and why?
So WebAssembly actually was thinking about including this talk, and I'm not including it because of time, so I'm glad you asked that. Yes, WebAssembly has 2 tiers. Originally it had 1 tier, which was just TurboFan. Then we introduced a compiler called Liftoff, which is very similar in many ways to CodeGen, I would say, in that it's just trying to stamp out code and doing it as simple as possible, kind of like stack-based register allocation. WebAssembly is a lot easier to compile because the bytecodes of WebAssembly are much lower level. So you can, if you have an addition and you know that this is going to be an actual integer addition, you can stamp out an integer addition machine code instruction and just do some fiddling with the registers to do
it's typed, right?
And yeah, exactly, and it's typed, right? So this is a lot simpler to do.
Yeah.
There is a WebAssembly interpreter called Drumbake, which is in the V8 source code. It's not enabled by default. The reason it exists is not because of actually participating in this tiering, but because we want to have some way of running WebAssembly if we can't generate machine code at runtime. So if we're on a platform that disallows it, for example, there's a YouTube app that I think runs on the PlayStation, which is not allowed to run machine code. This one would then have to use WebAssembly interpreter. This was contributed to us by Microsoft. It's not actually written by us, and it's not officially supported by us. But we have it there, just to have that copy upstream. They use it in Edge to be able to have to run in this jitless mode effectively for security reasons. You might think that having an interpreter would speed up this startup. But it turns like when we've tried to actually integrate an interpreter into that tiering pipeline, we found that, again, the WebAssembly bytecodes are very low level, so suddenly your interpretation overheads completely dominate your actual execution. I think Drumbake ends up being 20 times slower than Liftoff. And Liftoff can compile pretty quickly because it's really easy to compile. So if you compare it against this kind of like Ignition Sparkplug style approach, the positions of these in the trade-off graph get a lot closer in terms of, shall we say, compilation cost. But the compilation benefit of a Liftoff is so much higher on the graph that the interpreter is just not worth it. You might as well just race to the finish by compiling to Liftoff and running Liftoff. The sum of those 2 things is still going to be faster than the interpretation.
Mm-hmm. What about sort of a middle tier? Is there likely to ever be sort of a middle tier?
Between Liftoff and TurboFan?
Yeah.
The performance difference between those 2 is not actually huge.
Okay.
And it's not that huge because we're sort of receiving pre-optimized code.
Yeah.
So this is the high tier is really just there to squeeze out that extra, like a little bit of performance.
I'm one of the weird people who's generating relatively enough WebAssembly, but
sorry, man.
No, but I mean, even in my use cases, I've found that like when I disable TurboFan, the differences are not massive.
Yeah. I've seen numbers along the lines of like 10. I'm not directly working on WebAssembly myself, so I don't want to make it pull up too many numbers out of unspeakable places, but like it's on the order of magnitude more of like 10% and 10 times.
Yeah.
I was wondering whether there is actually something to optimize, in the WebAssembly. I mean, don't you have to somehow resynthesize what is going on, or
So yes, and there's actually getting more and more to optimize, funnily enough. So the first thing to optimize is register allocation. Because WebAssembly doesn't have machine registers, has virtual registers. That by itself is already actually a huge impact. Anyone who's done any kind of register allocation work will know how big of an impact on code performance that can have. What we're now getting actually is WASM GC, which is introducing garbage collecting style objects into WASM. And this becomes a compilation target of languages like Java and Kotlin. And Java and Kotlin, like, these actually need optimizers when they're running by themselves because of things like devirtualization. So these sort of optimizations now you want to do for the WebAssembly. If that WebAssembly is now interacting with JavaScript because it wants to, let's say, do something on the DOM on a page, then maybe it wants to do inlining of that JavaScript into itself. Maybe you want to inline WebAssembly into JavaScript, and vice versa. Like suddenly, maybe you actually want to be able to de-optimize your WebAssembly. So WASM linear, like not necessarily that much optimization outside of register allocation, maybe a bit of peeling, these sort of things. WASM GC, like you start seeing actual things that you need to optimize them.
Okay. Yeah, then you ask the question.
Thank you. Awesome presentation. Thank you. One question regarding optimization. Do you have kind of some ML-based optimization that you use in production? And if so, can you share some resources about it?
Actually, no. This is all artisanal, handcrafted human optimization. Even all the different heuristics, like we've thought about trying to get some sort of ML style model to figure out whether tiering is worth it. But honestly, like the black boxness of these makes these very hard to reason about. If we don't immediately get a good result, and we're like,
yeah, makes sense. But I saw some results, but it's kind of early results regarding the use of LLMs in phase ordering, something like that. But yeah,
it's not something that we've heavily really invested in. I'll be honest, like we haven't really experimented with it too much, because we've made a lot of these like actual compiler changes by themselves. A lot of the benefits that we get from the optimization as well is less from the kind of like classic optimization phase ordering kind of stuff. But obviously that provides benefit. But most of the benefit that we get is from better speculation.
Yeah.
And the speculation has to be interact with the runtime. And this is all like architectural design rather than classic compiler work.
Okay, that makes sense. Thank you. Awesome.
Okay, I still have two questions. I'm not sure whether
the configurate open source that's really
okay. So there's at least enough time. So the first question is kind of like an implementation question. You had this figure. I think it was very close to the end. There are no page numbers, so I cannot.
Oh yes,
not directed to the page numbers, but you had this figure where you said you had ignition, and then the bytecode was fed into Sparkplug, then into Maglev, and then into TurboFan. And it seemed to me.
You can keep asking a question. I'm listening.
Yes, it seems to me kind of strange that this is the one that you're feeding the original bytecode from into all of these cheap compilers, and there is only at the end you had Maglev also going into TurboShaft. So I think I remember even that the last Spark gave a talk about that like 12 years ago at Uppsala. That Sparkplug was like a predecessor, the template chip. That, I don't know what name of it, but it was collecting some kind of profiling information. So is there literally no information that is like carried on top of the bytecode?
No, there's plenty of information. Okay. Like the feedback vector that I was talking about, these data-driven ICs. These are actually mostly only collected by Sparkplug. So at this point, the interpreter first runs without feedback and without inline caches, because a lot of code only ever runs once. And if you only ever run once, then you don't get any benefit from caching. So we only allocate even these feedback vectors after 8 executions of a function, give or take, some adjustments for loops. And at the same time, we also compile to Sparkplug, because we're like, well, if we're collecting feedback, we might as well also start running in baseline code. So the majority of feedback collection is done by Sparkplug.
So there is another path where like this information flows also into Maglev. Yeah,
there's like a parallel path of a feedback vector, which is populated by ignition to some extent in Sparkplug, and then that feeds into Maglev and TurboShaft. And this is what all these actual speculative optimizations are based on. What I meant by this arrow was as a contrast against Crankshaft, where Crankshaft was consuming the AST rather than the bytecode. Using the bytecode as a source of truth for all subsequent compilers is, I should have mentioned this actually in the talk, I was mentioning it in my head when I was practicing, this was a huge benefit for keeping things a lot simpler and keeping things a lot more debuggable, because you had this one source of truth, which was relatively simple to comprehend, the bytecode, rather than a complex AST. And a lot of new features that were coming in were effectively syntactic sugar on the AST level, could be de-sugared into the bytecode, and then everything else didn't have to care about them. So that's why the bytecode is feeding into Maglev and TurboShaft. But yes, there's all the other information being collected as well. And if Maglev sees information that it didn't expect, that's when it de-optimizes into the interpreter. The interpreter then reruns that operation effectively, collects the feedback on it, and feed it back to the next optimization.
Okay, so that was the first part. And the second question I had was, so there, in certain respects, JSC is doing similar parts. So JSC also, I happened to drink beer with a guy who worked on JSC. It wasn't Fitzler, not the name. But he essentially said, 96% of the time the JIT doesn't even kick in.
Yeah.
But this was like 2013, so I'm not sure whether it's true. And it seems to me what you said is pretty much confirming this thing about saying, okay, like most of the time this is kicking in, so there is some interest in keeping this fast.
Yeah.
And so to me, I still like we are not sure what kind of Bedlam we're talking about, but the second one was Christian Bale, where I think the internet had a peak moment and it went downhill from there. So what kind of applications are really going into TurboLav? I mean, what is it
into TurboLav?
Yeah, so there must be some very long running, let's assume there isn't any Gmail, any full maps and stuff, but what kinds of typical applications are it?
Honestly, like that sort of thing, like let's say there's not those ones, then it's the other ones that do much the same thing.
Okay.
But yeah, like in all honesty, it's even if you load up like the trace that I took earlier, where I said that actually not much time to spend in TurboLav itself, or TurboFan itself. That was on, I think, CNN.com. And that's a heavy website, reasonably. Like it has to load ads, it has to do a bunch of stuff, it has to load images, it has dynamic, whatever. But yeah, even that one was not running much in the top tier. Something like Facebook, if they want to do dynamic loading of whatever, anything that's longer lived, effectively, and like you leave it as a background tab. Yeah. Google Sheets is actually migrating to WASM-GC now. The calc engine in Sheets is now fully WASM-GC, and the front end wants to move to WASM-GC modulo some like growing pains from having used JavaScript for 2 decades. But yeah, like a lot of actually, this is a good point. A lot of things that do need that sort of like top tier performance do actually start to move now to WASM.
But the thing is, then essentially you have like this kind of real web apps that end up in like the most optimum tier or the most optimal region. But then isn't the question? I mean, Phil Fitzler already had this fourth GL part that he said, he's going to make it a lot faster, and I think in the end it didn't work out.
Yeah.
But isn't then the idea that at the very end it's not about the code anymore, but it's some kind of data optimizations that you will have to do to make it still faster? I mean, is getting it faster still a goal, or is it already pretty fast anyhow?
It's still a goal, right? Like it's still like this push and pull between the client and the machine. Like yes, if you want to get a web app, like your super needs peak performance web app to run faster, like you will also need to do optimizations yourself. But that doesn't mean like it doesn't mean that you won't get another XYZ% from the actual top tier compiler being faster. It's not going to be a 10x improvement by any means. You're never going to get a 10x improvement from these things. But we sort of see ourselves as analogous to a CPU maker, effectively, where we might get a better, let's say, branch prediction or something, and it's not going to be huge improvement on code that executes, but it's going to be an improvement. And when you multiply that improvement by 3 billion users, maybe 2 billion that are actually running these big web apps, it adds up. if you have people who want to write their actual applications as web apps instead of as, let's say, mobile apps, then you will get benefits in, let's say, battery, right? So yeah, it's incremental improvements, definitely. It's never going to be order of magnitude improvements, but it's still worth investing in.
Okay, thanks.
There was another question over there. Yeah.
Yeah, I really captured in the talk. I would like to hear your thoughts about the debuggability like on a coffee break. But you mentioned that you do like code patching at a certain point. Have you considered instead of like code patching, like a different approaches, for example, like a function table similar to like what Linux does with PLT and ROT for dynamic loading and replacing functions, where you can just instead of like patching different locations, and the function is called, you actually have like a dot table or a table of functions that stores the pointer to the desired function and a small stub, like a send stub that resolves it. So when you're replacing or doing like de-optimization, instead of like patching for different locations, you just swap the pointer at.
So when we do de-optimization, we don't actually patch the entire code to get de-optimized. We have two copies of the code, like one that's the non-optimized one and one that's the optimized one. And the optimized one is like not patchable into the de-optimized one. We've done all sorts of transformations on this, reorderings of things, like things that we've assumed have no side effects. We'll reorder before things that did have side effects. All these sort of things. The de-optimization is really a translation of one stack frame into another stack frame. The patching that we were doing was for individual operations rather than for the entire code. So we would observe like this one location. Like the interesting thing about inline caches is that they're inline to the operation location, not inline to the object. So if you, let's say, changed the type of one of your fields in your map, that wouldn't necessarily de-optimize accesses to other fields of that map. It would just de-optimize accesses to that first field again. But there is something similar that we do for the actual entry point into a function. So the optimization is on a function granularity. And if we optimize something that is the entire function and whatever it inlines, and the entry point decides whether it goes into the interpreter or into that optimized code or Sparkplug. That entry point is a table. And that table allows us, like if we have multiple copies, instances of the same function, to optimize all of them at the same time and de-optimize all of them at the same time. Another benefit is for security. These functions are stored in the V8 heap, the actual like JavaScript visible object. So if you have some sort of out of bounds access inside of the V8 heap, you would be able to change what the code pointer of that particular function is if you have a direct code pointer there. If we've now just got indices into this table, then we've got like a form of forward CFI where you can only get your JavaScript function to call into other JavaScript functions. You can't get it to call into arbitrary code. And we make sure that any sort of like out of bounds accesses within the V8 heap stay within the V8 heap because of a project called pointer compression, sandboxing. There's all sorts of interesting presentations and blog posts about that.
So for example, like transitions between like native code and then back to the interpreter and are possible.
Yeah.
So that is like, for example, V8 does when it needs to transition from like, machine code back to the VM because registers doesn't have necessarily the same value.
No.
Do you have like some prologue and epilogue that you have to admit and what that has to do? Ensure like the safe back to
not exactly. There's attached to the code, but for every potential location that could de-optimize, there's an attached effectively translation table, which maps all possible values that are currently available into the equivalent values in the interpreter, and you do the stack frame to stack frame translation. And this is more complex actually than it might sound because we might have eliminated some objects through escape analysis, that sort of thing. So this will also include instructions on how to rematerialize objects that you should have allocated in the first place. And it's effectively a whole bytecode in itself, like a stack frame generating bytecode. But yeah, that's the way that it's encoded.
If I understood correctly, you're also benchmarking on live websites.
Yes.
Or
Ish. Yeah, well, website recordings. Yeah.
You have been doing that for a while, right?
Mhm.
Have you noticed any major changes kind of in kind of code structure or things that are relevant for your compiler over time?
Well, because they're website recordings, we don't notice any changes in them.
Okay.
But we do also.
You're not updating them every half year.
It's a surprisingly large effort to update these things. Like you wouldn't think so, but because you actually want to interact with these websites, you want to scroll, you want to click. Like each update to these means actually doing those operations. If you need to log in, then you need to figure out how to skip that login in the actual recording. So all of our recording is actually really old. And not anymore, man. This is the period of like laying off tech employees. What we're trying to do instead is generate synthetic workloads that kind of behave like real websites and add them to benchmarks like Speedometer.
But what I wanted to really get at is whether you already see any kind of effect of slop on the internet changing what you would need to optimize.
To be honest, like what we've mostly seen is human slop, because like AI hasn't been around long enough to have a huge impact on like the largest properties of the world. We also have a real world metric tracking, and what we've noticed with the real world metric tracking is that whenever we make our stuff faster, websites get slower, and the actual real world metrics stay flat because everyone has like a performance budget effectively, and the work that we invest helps other people spend less on engineers, which I don't know, like we'll still have to keep paying for making things fast. But yeah, we do observe actually like things getting slower, we assume, because we're getting faster and performance stays the same. And if we look back on historical Chrome versions, loading current websites with old Chrome versions, we see those websites loading slower than they do now. And we've got like this wonderful video where we've got like every 2 milestones of Chrome loading the same page side by side, and you see the page pop up like this, here, like practically linear. Yeah. But AI slop hasn't hit us hard there yet.
So I think it's an instance of Wirt's law, where it's from 1995. It says that hardware gets faster, slower. Software gets slower faster than hardware gets faster, and this is exactly what you see.
Yeah, exactly.
What you see too. Yeah. And there was I think we call it the final question from Patrick, and then we head off to coffee break.
I just wanted to ask, was there anything written up yet about the new this pointer-free IR, or do you have any resources
for TurboShaft?
Yeah.
Yeah. So we have a blog post I mentioned earlier about leaving the seed notes.
Okay, yeah, I've seen that, but it doesn't. I don't recall that went into details about what the new IR looks like. Does it? Maybe
it doesn't. Maybe it doesn't. Like,
I remember it being like, "Hey, we're moving away from CNOs." Yeah. So I guess I'm just curious if you have if there were any existing IRs that you have. I mean, like I remember hearing that Luajit had also a pointer-free IR that Michael attributed a lot of Luajit's performance to. So I'm curious if there are any other sort of examples, things that might be interesting reading if someone were interested in doing something similar.
Off the top of my head, if that blog post doesn't have it, then I wouldn't be sure. I'm probably written something else.
I just forgot that it was in there.
To be honest, like it's not like I don't want to say that it's not a huge innovation because it is interesting, but it is just pointers just within a different address space.
Okay.
Right.
I mean, I guess I'm wondering if there's other details about what's new in the IR, or whether it's just a CFG with offsets rather than more noise.
No, I mean it tries to be compact. It's fully linear. Basic block boundaries are encoded as offsets within that linear space. These sort of things. I'm sure there's design docs, and I'm reasonably sure there's public. I can probably figure out if there's a way I can share one, but I don't have it off the top of my head.
I can dig around a bit more.
Okay, thanks. Leszek, thanks for the talk and the questions.